Hey everyone, and welcome. Today we're jumping into a really cool application of integral calculus, figuring out the center of mass. All right, let's get right into it.
So, picture this. You cut some random, kind of weird shape out of a piece of cardboard. Now, is there a single magic spot where you could put your finger and the whole thing would just balance perfectly without tipping over? Well, that's the exact question we're going to answer today with a little help from calculus.
You know, that balancing point actually has a name. It's called the center of mass. Or, if the object has the same density all the way through, we call it the centroid. You can think of it as the geometric heart of the object. But to find it with math, we first have to understand the forces that are at play here.
And that brings us to this idea of a moment. A moment is really just a way to measure an object's tendency to rotate around a point. The easiest way to think about it is a seesaw, right? A heavier person sitting closer to the middle can be perfectly balanced by a lighter person who's sitting way farther out. That's because their moments are equal. We're going to use that exact same idea, but for every single point inside our shape.
So, how in the world do you add up an infinite number of points to find the total moment? Well, with integrals, of course. So let's open up the toolkit and see the formulas we're going to need.
Okay, here they are, our two key formulas for the centroid coordinates, which we call x bar and y bar. Now, look closely because the really important thing here is the difference in what we're actually integrating. For x bar, our horizontal balance, we're basically adding up the moment of each tiny vertical strip. That's its position, x, times its mass, which we can think of as its height, f of x. But for y bar, the vertical balance, the formula looks a bit different, doesn't it? We're integrating 1/2 of f of x squared.
And here is a fantastic little memory tip to keep these two straight, because honestly, this is where people get tripped up all the time. For x bar, just think of it as the strip's position, x, times its height, f of x. Simple enough. For y bar, that weird 1/2 f of x squared term, that actually comes from finding the average height of that very same strip.
All right, theory's one thing, but the best way to really get these formulas is to see them in action. So let's start with a nice, simple, familiar shape, a triangle. Here's our first problem. We need to find the balancing point, the centroid of this triangular region that's defined by the line y equals 2x, the vertical line at x equals 1, and the x-axis itself.
Okay, the process here is super methodical. You just follow these 5 steps. Step 1, we find the total area A by integrating our function from 0 to 1. Turns out the area is 1. Easy. Step 2, we calculate the moment about the y-axis. Then for step 3, we find our x-coordinate x bar by dividing that moment by the area, which gets us 2/3. Now we just do it again. For step 4, we calculate the moment about the x-axis using our second formula. And finally, step 5, we divide that moment by the area to get our y-coordinate y bar, which, hey, also comes out to 2/3.
And there we have it. The centroid, the absolute perfect balancing point for our triangle, is located at the coordinate 2/3, 2/3.
But wait, here's the really cool part. This isn't just some random answer for this one triangle. What we've just done is actually show a universal property of geometry. The centroid of any triangle is always located 2/3 of the way from any corner to the middle of the opposite side. We just used calculus to prove it. How cool is that?
Okay, so triangles are great, but the real power of calculus is that it works for all sorts of curvy, complex shapes. So let's level up and see how this method handles something a bit more interesting.
Our next challenge, find the centroid of the area underneath a parabola, specifically y equals 4 minus x squared, but only the part that's in the first quadrant. The shape is totally different, but you know what? The method is exactly the same.
And yep, once again, we just follow the exact same recipe. First, we're going to integrate the function from 0 to 2 to find the total area. Then we just use our two formulas to calculate x bar and y bar, plugging in 4 minus x squared wherever we see f of x. Now, the algebra for the integrals might get a little bit messier, but the process itself, it doesn't change one bit.
So, after we crunch the numbers, we find that the balancing point for this little piece of a parabola is at 0.751.6. Seriously, if you were to cut this shape out, that is the exact spot where you'd put the pin to make it balance.
So far, we've only been talking about these continuous shapes where the mass is spread out perfectly evenly. But what happens if our system is made of separate, individual chunks? You know, like planets in a solar system, or a few weights on a barbell.
Let's look at a really simple one-dimensional problem. Imagine we have 3 masses on a line. We've got a 2-kilogram mass at position 1, a 3-kilogram mass at position 2, and then a much heavier
5 kilogram mass way out of position 6. Where's the balancing point for this system?
Well, for these separate, discrete masses, the logic is exactly the same, but the math actually gets way easier. Instead of doing a whole integral, we just sum things up. The formula is just the sum of each mass times its position, all of that divided by the total mass of the whole system.
For the system we just looked at, the total moment adds up to 38, and the total mass is 10 kilograms. So we divide them and we get our center of mass. It's at position 3.8.
And if you think about it, this should feel totally right. The balancing point isn't just in the geometric middle. No, it's been pulled away from the lighter masses and shifted over towards that much, much heavier 5 kilogram mass. The math just confirms what our gut tells us.
So, we've gone from the simple idea of a balancing point all the way to using calculus for complex shapes and even looking at systems of separate masses. But we've been stuck in 2 dimensions this whole time. So that leaves us with one last thought. What kind of tools would you need to find the center of mass of a solid 3-dimensional object like a pyramid? Well, that's where this journey heads next. Thanks for tuning in.